तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we have understood how a CMOS inverter functions, both as a logic circuit as well as an amplifier. Now let us see an example, example 18, a CMOS inverter with Kp equal to 1 milliampere per volt square and Kn equal to 4 milliampere per volt square, Vtn equal to 1 volt and Vtp equal to minus 2 volts, uses 10 volt supply. Obtain its transfer characteristic. Now let us proceed with that. First, this is the CMOS inverter. When Vi is 0, output is going to be at 10 volts. The transistor is T1 is not conducting, so this is at 10 volts. This is going to remain at 10 volts up to Vi of 1 volt. That is, after that, okay, this Vt is 1 volt. After that, this transistor starts conducting. It will come into the current saturation region. So, T1 is off up to this point. Thereafter, T1 starts conducting. T2 meanwhile is in the triode region. So, this is the region where T1 is off and T2 is in the triode region. This is the region where T1 has come to current saturation region and T2 is in the triode region. So, this is one important point, okay, 1 volt. Then T2 will come into the current saturation region when this will go on. This is that characteristic curve where IDS2 is made equal to IDS1. So, that is the equation that it gives us. IDS2 is obtained from the fact that it is in the triode region, IDS1 is obtained from the fact that it is in the current saturation region. And we have at a point V naught equal to Vi plus 2 volts, Vtp being equal to minus 2 volts, okay, at a point when Vds magnitude becomes equal to Vgs minus Vt magnitude. Okay. So, that information gives us V naught equal to Vi plus 2 in this case. So, that characteristic obviously will start with this 2, this is the intercept when Vi is equal to 0 and go with a slope of 1, and where will it intersect? When, of course, that we have to find out, okay, when this enters the current saturation region. So, we will leave it like that. We do not know where it enters the current saturation region. So, the other line is V naught equal to Vi minus 1 corresponding to this transistor going to triode region. Again it is this Vds which is V naught itself, okay, is equal to Vi minus 1. That is the region where it is entering the triode region. Now, in between we have both transistors in current saturation region. Therefore, we have Kp which is 1 into, now this is important, Vgs minus Vt, which we are going to always refer as Vsg. Okay. So, 10 minus Vi minus 2 volts. Okay. Otherwise, it would have been Vi minus 10 plus 2 volts. Okay. So, this square equals K of the other one 4 into Vi minus 1 square, which is nothing but 8 minus Vi, remove the square, this is 8 minus Vi, okay, square root of 4, 2 into Vi minus 1, from which we get 2 Vi plus 1 Vi, 3 Vi equals to how much? 3 Vi equals 8 plus 2, 10 volts. So, Vi equals, how much is it? 10 by 3. Is this clear? So, this is 10 by 3 is 3.33 so on, right. So, somewhere here this is 3.33. Okay. So, we can draw that somewhat more carefully. Now, at Vi equal to 3.33, there is a transition and it is having infinite slope, where both the transistors are in current saturation region. So, if Vi is equal to 3.33, then this voltage at which this transition takes place is V naught equal to 3.33 plus 2 volts, that is 7.33. This is 7, so this is about 7.33. So, you can see that from that point to this point, it is going to be a nonlinear curve. Okay. So, this corresponds to 7.33, V naught equal to 3.33, okay, sorry, 5.33, right. Vi is 3.33, this is 3.33 plus 2, that is 5.33, sorry. This becomes 5 somewhere here, 5.33, and this one is 3.33 minus 1, which is 2.33. At 2.33, and again it is going to deviate. So, this region from 2.33 to 5.33 for a region of 3 volts, okay, which is strictly speaking magnitude of Vtn plus magnitude of Vtp, 1 plus 2, okay, 3 volts here. It is having infinite slope. Thereafter, up to 8 volts. What is 8 volts? 10 minus magnitude of Vtp, 10 minus 2 volts, 8 volts. Okay. This story will go on. After this, transistor T2 will go off. So, this is the complete characteristic of our CMOS inverter. Okay. where if you draw a 45-degree line, 45-degree line, what is the slope? Tan 45, that is -1 here. You can draw a similar line here. It is within this region that we say that the transistor CMOS inverter is in the active region, gain is greater than 1. Beyond this region, okay, it is not in the active region, it has gone into what? One of the two saturation states, either this or the other one. So, these are important in digital circuit in defining what is called as noise margin. Okay. So, the point at which dV0 by dVi becomes equal to -1. You already know V0 versus Vi characteristics from the equation of what? Currents being equal. Okay. So, from that equation you can obtain dV0 by dVi equal to -1, you substitute that and find out the point at which this occurs. Okay. This I am going to leave as an exercise for you. Okay. In this region, find out dV0 by dVi from the expression for V0 versus Vi, and then substitute equal to -1 and find out the point V0 and Vi at which this happens. So, further, when it is in the active region, what will be the gain? Infinity. That is only when we are assuming that RDS of these transistors are infinity. Okay. Now, if you take finite RDS, there is an RDS1 here, this is RDS2, RDS1 and RDS2, they come in parallel, and therefore, the gain of this is this is going to be replaced by a current source which is Gm into Vi. This also is going to be replaced by another current source Gm into Vi. As far as signal is concerned, whether you use NMOS or PMOS, it does not make any difference. Okay. So, these two are working in parallel onto the same load, and the load is RDS1 parallel RDS2. And what is the effective current? 2 Gm times Vi. 1 Gm times Vi due to this, another Gm times Vi due to this, right, assuming that both the transistors are operating at the same current, that is true. Okay. So, Gm1 and Gm2 may be different because Ks are different. So, essence Gm1 plus Gm2 into RDS1 parallel RDS2 is the amplifier gain when RDS1 and RDS2 are not infinite. Is this clear? So, these two amplifiers are working in parallel onto a common load which is RDS1 parallel RDS2. Since they are working in parallel, the effective Gm will be Gm1 plus Gm2 into Vi. So, we have understood how this can be used in an inverting amplifier with this kind of gain, how it can be used as a digital inverter, and we also know how this current varies with respect to what? Signal Vi. Now, you can see that the current in this under this situation is given by this 1 into 8 minus 2 whole square or 4 into 8 minus Vi whole square or 4 into Vi minus 1 whole square, with Vi is equal to 3.33. So, that is the maximum current that will flow in a CMOS inverter, and gradually it will go to 0 on either side. So, this is the point where the current is going to be maximum. We will say current plot. The value of this is 8 minus 3.33 whole square. Okay. So many milliamperes. How much is it? 8 minus 3.33 whole square, that is 22.1 milliampere. So, substantial amount of current flows. Okay. So, then again it becomes 0 when this transistor goes to off, and again it becomes 0 when the other transistor goes to off state. So, this is the nature of current waveform. This is 22.1 milliampere. Now, I am going to show you the actual components like the transistors, the active components, as well as the op amp that we commonly use in our circuit design. So, we have here an operational amplifier 747, very general purpose operational amplifier, very commonly used. This is what is called dual inline package. I mean, this can also come in what is called TO5 package, which it looks like this. This is dual inline package. There are 14 pins here. 747 comprises 2 operational amplifiers, identical operational amplifiers. Now, each operational amplifier will have 2 input terminals, differential input, okay, 1 output terminal, so 3 terminals, and 2 power supply terminals for the dual supply to be applied. So, 2 plus 1, 3 plus 2, 5 terminals essentially, and if there are 2 such op amps, we will have 10 terminals taken care of, and in this 14 pin we have possibility of what is called offset compensation, about which we have also discussed. So, 2 terminals for one op amp and 2 terminals for the other op amp for offset compensation. Okay. So, that forms the 14 pin base, and the base diagram we can see here, top view of LM747, 2 op amps A and B, the 2 input terminals, 1 output terminal, okay, of A, 2 input terminals and 1 output terminal of B. This is the non-inverting terminal. We know how to find out non-inverting terminal and inverting terminal in an amplifier configuration. Okay. That means phase shift from here to here is 0, phase shift from here to here is 180 degrees, and this is the negative supply. We have 2 terminals for the, what is that, positive supply, one for A and one for B separately, common negative supply, and then we have 2 terminals for offset compensation for each of these, okay, op amps. Now, as far as the other transistors which are going to be used within these op amps, basically these are bipolar transistors. Typically a single discrete bipolar transistor looks like this. This is BC107, a small signal amplifier stage you can build, okay, using such a transistor. Now, normally the projection, okay, is the emitter or the source in the case of a field effect transistor. There is a small projection, I do not think you can see that, okay, in this metal projection in this, which is the emitter or the source in the case of a FET. And you can also identify the base. Base is the, it forms a triangle, and base is the, okay, center, okay, or the apex of the triangle, and the other terminal is the collector. That is how you can identify emitter base collector of a transistor. These 2 are NPN and PNP pair, which are commonly used for power application, which we will see later. This is called complementary pair, NPN PNP pair. Okay. Low power amplifier applications, these are used. Then we have another unit which we had discussed in the class, the differential amplifier. This comprises a pair of matched transistors with a current source, okay, with all the biasing incorporated in it. Collector loads are kept open. So, the two collectors are open collectors, so that you can connect whatever you want. So, CA3028 is a very useful differential amplifier used for both video as well as wideband and high frequency IF RF applications. This also we will see later how this differential amplifier can be used. This of course is a junction FET. Once again we have three terminals, the projection being the source, okay. Then we have the gate and the drain. So, these are the active devices which have been displayed here. The application of these, the biasing of these have been discussed, and the use of these in amplifiers we have discussed, okay. And how to design a high gain amplifier and make an op amp out of it also has been discussed so far in our course program, okay. In the next one we will discuss further about negative feedback, what is positive feedback, what are filters, oscillators, then modulators, demodulators, regulators, voltage regulators, okay, power amplifiers and things like that. So, this block is going to be over with this basic knowledge about active devices, diode, use of these diodes in variety of applications, use of active devices, okay, in amplifiers, building amplifiers, biasing mainly, design of operational amplifiers, basic digital inverter. Okay. At the end of this part 1 of analog circuits, I would like to indicate that laboratory experience is part and parcel of this program. On all the examples that have been given, worked out, can be tried out experimentally in the laboratory. I am, as an illustration, taking a common emitter amplifier as depicted here. Okay. This has been designed, this has been wired up for you, and we will presently see the amplifier demonstration. Okay. Now, 15 volts is applied to a transistor amplifier with R1 equal to 10K, R2 equal to 42.9. So, the voltage at the base, okay, quiescent voltage comes out to be 2.84 volts calculated. If you take 0.6 as the VBE, the voltage at this point comes out as 2.24 volts. And we have introduced 2.2K to ground emitter resistance, and therefore, current in this is roughly 1 milliampere. So, this transistor has been biased to operate at 1 milliampere. This has been bypassed by the emitter bypass capacitor of 100 microfarad. So, this is a common emitter configuration biased at 1 milliampere. Because it is 1 milliampere, 6.2 volts drop will occur across RC of 6.2K, and 15 minus 6.2 volts is roughly 8.8 volts. 8.8 volts minus 2.8 is roughly going to be 6 volts. That is the VCBQ. So, IEQ is 1 milliampere, VCBQ is 6 volts, RE, which is VT over IEQ, is roughly equal to 25 ohms, and therefore, G minus GMRC, which is the gain of the common emitter amplifier, is minus 40 millisiemens. For 25 ohms, it is 40 millisiemens into 6.2K, which is minus 248. Now, we will see, right, whether in our experimental setup we get nearly this kind of gain, and what kind of waveforms we see here and this place. To the experimental setup, we have here Padmavati, who has wired this circuit, and we have an oscilloscope to see both the input and the output waveform. You can see the output and input waveform, okay, and there is a phase shift of 180 degree. As you can see, when one is going to the, this is the output, okay, point, through the capacitor it has been taken, input is here. So, these 2 points, the waveforms are shown in the oscilloscope there, yeah. So, you can see that there is a phase shift. When the voltage at the input is increasing, output is decreasing. Can you see that? And also corresponding scale, if you read out, the input is about 2 millivolts, okay, and you have got a gain of about 250, so output is about 0.5 volts, okay, peak to peak. So this is depicted there on the oscilloscope. If you couple it along with the scale given, you will see that the gain is exactly equal to 250. Further, we will check the operating points. Now Padmavati will show us using a DC multimeter the potential at the base, which should be 2.84. Let us see how much it comes. The resistors are all 5% resistors, so there might be some small variation in this. You can lift it up and show. Yeah. So that is the voltage, 2.75 instead of 2.84, which is acceptable. And now she will connect it at the emitter. There should be a 0.6 drop, 0.6 volts drop. Yeah. So that is the potential at the emitter, okay, at this point in the circuit. Because of 0.6 volts drop, we have the potential at the emitter. Yeah. Okay. And then we have the potential at the collector. Once again, she will now connect it to the collector terminal, which should be around 8.8 volts DC potential. So you have that voltage 8.68, which is pretty close to 8.7 volts, okay, which is pretty close to the expected value. Now the DC potential, after verifying, you can check the thing for AC signal. Always first verify the operating point. The transistor should be operating in the active region, okay, and it should be operating at the point at which you have designed it. That is most important. Then only you apply the signal, okay. Then you measure the signal gain. That came out as, okay, 250 minus 250, okay. Now we will illustrate the last signal effect. Okay. Now that this is biased to VCBQ of 6 volts here, and current I is about 1 milliampere, due to the limits. One is the transistor going to off, okay, that 1 milliampere into 6.2 K. So it is one side 6.2 volts, on the other side it is again 6 volts. It is almost symmetric swing possible. That means both saturation limit as well as cutoff limit should begin almost simultaneously. So let us keep increasing the signal. Now, okay, now Padmavati will increase the signal level slowly and show you what happens to the output. Distortion will occur, okay. You will see that distortion is going to occur. Yes. You can see that the top portion of the waveform is broadening out, okay. Lower the signal level further, too much signal. Further reduce it, reduce the signal level. That is the thing. You can now, you can see the distortion. This is the exponential waveform, right? Because the current is exponentially related to the input voltage, we have the top portion broadening and bottom portion narrowing, right? Now please increase the signal level slowly, so that slowly, there you can see, just decrease it little bit, you can see the lower portion, okay, going to saturation, right. Upper portion corresponds to cutoff, okay. So, that is the signal limit. Actually, the signal swing comes out as 1, 2, 3, 4, 5, very nearly 5, about 10 volts. So, around 10 volts or so. I mean, actually signal can be further increased. Right. Now, I would like you to also see the effect of opening the capacitor. This is similar to the circuit that we have discussed in the case of differential amplifier, where the emitter resistance was increased. Apart from this 25 ohms, now it is equivalent to putting 2.2 kilo ohms in series. So, we will open the 100 microfarad capacitor and see the same effect. Now, the gain will be much reduced, because instead of Gm as 1 over small re, we will have 1 over capital Re coming into picture, which is 2.2 K. So, that is 6.2 K and that is 2.2 K, very nearly 3, gain of about 3 you get. So, this we can see. Here you will also notice that the transistor takes very little of voltage, most of the voltage, input voltage is taken by 2.2 K, and therefore, there is very little distortion. This we will interpret in a different manner later in our lecture on negative feedback. So, when the input voltage Vi is applied now, that is partially falling across the transistor and partially across the 2.2 K, and what is coming across 2.2 K is the considerable part of signal, because the transistor takes only corresponding to 25 ohms and this takes corresponding to 2.2 kilo ohm in series with 25 ohms, and therefore, most of the input signal is dropped here. That is what we will see. Now, Padmavati will connect the input, the same input voltage has been connected, and you will see the output is going to be not 250 times the input, but about 3 times the input. Let us see the experimental this thing. See on the oscilloscope now very carefully that the input signal level, and she has put both the knobs at the same, almost same sensitivity, and therefore, you can see the output and input are almost of the same magnitude, except for one scale difference, which indicates that there is a gain of merely about less than 3, and the phase shift is 180 degrees. Now, let us increase the signal. Now, you will see that there is very little distortion, because the voltage, input voltage has dropped across 2.2 K instead of across the transistor, which is a nonlinear device, and this has become almost linear. So, the DC voltages remain the same. Now, we do not have to bother about the DC voltage, that remains unaltered. There is no distortion. DC voltage, whether it is small signal or low signal, remains the same. Unlike the other situation, the DC voltage is going to change because of distortion. Here, the DC voltage will remain the same. Now, input signal level, she will increase. Oscilloscope, you please concentrate on the oscilloscope. Focus on to the oscilloscope. Increase the signal level until distortion starts. Further, now you see no distortion at all. Now, distortion will occur only due to cutoff and saturation. Other distortion which has earlier occurred due to nonlinearity of the device disappears. This is because it has been made linear by putting a series resistance of 2.2 K in series with 25 ohms of the transistor. So, just increase the signal level. Yes. Decrease now. Now, you see, when it goes to saturation, the transistor is a point. Therefore, the input signal simply comes at the output. Earlier also it was coming, but input was very small compared to output. But now input is comparable to output, and you will see at the point of saturation the phase shift is the same as that of the input. Okay? Do you see at the bottom line you will see the top of the signal appearing, making an appearance. So, that is when the transistor has gone to saturation. Okay? At the cutoff, of course, supply voltage is going to limit. Now, if you increase the signal further, let us brute force. You see the top is chopping off, right, very clearly indicating that it is going up to supply voltage. In the bottom you have the transistor deep in saturation. Okay? So, this illustrates very clearly the signal limitation. Okay? Reduced so that it just enters the now just enters the nonlinearity. It should just enter. We keep on increasing the signal further, just stop there. Now, the peak to peak signal is the limit that you have not really earlier obtained, because the input signal is also going to reduce the output swing. Input is increasing when the output is decreasing. That way this is the signal swing. This kind of signal evaluation we will be doing again later when we discuss negative feedback circuit. So, in analog electronics part 1, which we have covered through a series of about 38 lectures, we have covered starting with diode as a 2-terminal element, one port, 2-terminal element, and its applications. In diode function generators, in voltage doublers, rectifiers, power supplies, and Zener regulators. Semiconductor diode applications as a temperature sensor and its large signal and small signal properties. Then we had discussed about two-port theory as a prelude to control sources, wherein we had discussed 4 types of control sources: voltage control voltage source, current control current source, voltage control current source, current control voltage source, as nothing but amplifiers. Idealized amplifiers are these control sources with parameters, 2-port parameters, which are H, Y, Z and G. We understood how to use these parameters in defining these ideal sources. What are non-idealities, and how to evaluate the input resistance, output resistance and transfer parameter in these amplifiers. Is 2-port network theory. Then we went over to actual active device, 3-terminal device. Transistor. First we took up bipolar junction transistor and defined transistor action as that will take place when collector base junction is reverse biased, emitter base junction is forward biased, IC is equal to alpha times IE, alpha being made pretty close to 1. That is the important equation in bipolar junction transistor. So, GM of the bipolar junction transistor we said is equal to Vt divided by IEQ, where IEQ is the operating current of the transistor, Vt is about 25 millivolts, Kt over Q at room temperature. Then we went over to the common emitter amplifier, biasing using single supply, dual supply, a reliable way of biasing, fixing up the emitter current that it is, right. That reliable way of biasing is fixing up the emitter current. Then evaluation of gain of common emitter amplifier, input resistance and output resistance, the parameters of amplifiers. And then what is the effect of large signal? What is meant by small signal? When does distortion occur? Because of the nonlinearity of the device. So, how to evaluate distortion? We discussed this. Then we went over to field effect transistors, junction field effect transistor and MOSFET, how this is going to be discussed in terms of enhancement type of operation and depletion type of operation, okay, and how JFET is a depletion type of field effect transistor, and what is pinch off voltage, what is threshold voltage, all these factors we had discussed, and the square law, okay, of current with respect to input voltage of the MOSFET has been highlighted, and what is triode region and current saturation region has been discussed. Then how common source amplifier similar to common emitter amplifier can be derived, and how using single supply and dual supply you can bias in an identical fashion the MOSFETs. Now the source current being fixed, okay, and how to evaluate the gain input resistance and output resistance from the small signal equivalent circuit of the field effect transistor, which is almost exactly same as that of the bipolar junction transistor. Okay. It is VBE is the input voltage, GM times VBE is the current source current in the case of a bipolar junction transistor. If it is VGS as the input voltage, GM times VGS is the current of the MOSFET or JFET, and each of these current sources can be shunted respectively by RCE and RDS respectively in the case of BJT and FET, and therefore the equivalent circuits are similar, except that as far as bipolar junction transistor is concerned, at the input it is not an open circuit, it has an input impedance which is RBE, which is RE into beta plus 1 approximately. So all these things we have discussed, and then went over to getting rid of coupling capacitors and bypass capacitors, and coming up with a novel configuration which is universally being used in place of all these discrete circuits, and that is the differential amplifier. Okay. So we said how this facilitates, okay, getting rid of bypass capacitors, and how using dual supplies we can also get rid of input coupling capacitor, and how by direct coupling we can get rid of coupling capacitor from stage to stage. What are the disadvantages associated with direct coupling? What sort of signal limitation will occur when NPN transistors alone are used? How NPN PNP combination, okay, helps us in avoiding what are called as level shifters, okay, and then we went over to design of an operational amplifier, which is nothing but a cascaded version of differential amplifier, okay, 2 stages, so that in all these op amps, okay, we always try to increase the forward transfer parameter. Therefore, we get 4 types of op amps corresponding to the 4 types of sources or amplifiers which we have discussed, which are called operational voltage amplifier, operational current amplifier, operational transconductance amplifier, operational trans resistance amplifiers, wherein always concentration is over improving the forward transfer parameter by cascading. Okay. So we had concentrated on design of operational voltage amplifier, and we saw how we can give an equivalent circuit for the op amp, okay, operational voltage amplifier. Then we went over to MOS inverters, which do not have to necessarily use any resistor at all, and the MOSFETs themselves are being used as resistors. We had also seen when discussing about FETs how FET can be used in the triode region as a linear resistor. So this formed the complete discussion of amplifiers as well as diode, okay, part 1, and the part 2 is going to be further discussing about other aspects of amplifiers, negative feedback, positive feedback, frequency limitations, wideband amplifiers, okay, and then filters, oscillators, and then modulators, demodulators, automatic gain control, AVC, phase lock loop, etc.